Ladies and gentlemen, Gateways here, and I will explain you how to learn about the swarm robotics. Follow me in this tutorial. What is the core foundation of the swarm robotics? Well, the core foundation for swarm robotics is that we study the large number of simple agents to communicate with the environment in a smart collective behavior. The key concept of these swarm robotics is that they are decentralized, meaning they don't need a single leader or a brain, and they only do a local interaction, meaning they can only sense their local neighbors or what is the close to them. Because of this, they are highly attributable entities, which means they don't need to cost as much. Meaning you can lose some few, but you can also replace with more agents. In spite of that, you can also have an emerging global patterns with few local rules. For example, how ants make a bridge, how wasps build a nest, how bees build a nest and collect wax, and all this. These are simple behavior, but these simple behavior can accumulate into a complex one. And the scalability, as I said before, the scalability comes from the attributability, which means if one unit fails, you can have the operation won't stop. And if you're adding more units, it will face no bottleneck. It will face no computational bottleneck. So, what is the swarm advantage? The first advantage, as I said before, is robustness. Because there is no central controller, the failure of a single robot to even a significant percentage does not lead to a mission failure. The swarm is inherently fault-tolerant and adaptive. And the second advantage, that they are flexible and efficient. Swarm agents can reallocate tasks dynamically based on local environmental changes. They excel in environments where communication is unstable or GPS is unavailable. It's basically like that, because since they only sense closely to their neighbors, they can communicate with the neighbors, and since they are in a massive number, this communication can reach over long distances. But where does all these swarm technologies comes from? Well, it comes from biologies, as I said before. Birds, bees, ants, anything that crowds together in a massive number. So it says the wisdom of the crowd. Engineering swarm begins with observing nature. Bird flocking and foraging and bees clustering provide the blueprint for decentralized coordination. Natural system demonstrate how simple local rules, like following a pheromone trail, leads to the optimized discovery resource across vast area. This is basically an A-star algorithm, but better, because if a single ant finds a root, it will call the other mates. Sorry about my hair, it's kind of itchy, but as I said before, if an ant finds food, it will call the other ants, and they suddenly go towards the food and pick it up. Over time, that route will change its course until it becomes the most optimal route to reach from the nest to the food source. So, what is the most simple algorithm for the swarm simulation? It's the Boyd's algorithm. Founded by Great Reynolds in 1986, which defined the flocking through three simple steering rules. Separation, avoid crowding neighbors. Alignment, steer towards average heading. Cohesion, steer towards center of mass. Here's an example of alignment, which allows you to steer a single agent towards a local flockmate, the average mass of the local flockmate, the centroid of the local mass. Then we will also talk about the essential swarm algorithm, which is stigmergy, indirect coordination through environmental changes such as pheromone trails or block placement in construction. This is an external stimuli. For example, you sense a pheromone, or sense some light, or you sense some touch. Is there something involved? Is there an obstacle? So we have to change. This is one way we will stimulate the swarm behavior. Second is the consensus, which means it have some protocols that allow a swarm to reach a single opinion or a goal through local voting and agreement mechanics. Which means you have some protocol, you have some fixed protocol. For example, go from point A to point B, but avoid point C because it's very dangerous. Then they all agree, yes, let's do this, because that's a universal. That's something everyone agree on. But if it has D, then someone can choose point D because it's not dangerous, but it's long tedious. But it also have some optional way to collect more food. Sorry about my eye, because it's summer, it's quite hot. And finally, we have particle swarm optimization. Agents move towards the individual best and a global best known position. This particle swarm optimization is similar to genetic algorithm, where it also find the global best. It finds both the local best but also the global best. Simulation first. Why do we simulate? Physical swarms are expensive and difficult to maintain. Simulation allows rapid testing of algorithms with thousands of units. Here's some simulation. We have Argos, the industry standard for large-scale heterogeneous robots. Then we have Rebots, high-fidelity physics for precise robot environment interaction. Then we have NetLogo, excellent for beginner to visualize agent-based modeling. Swarm Robotics has lots of research platforms. For example, Killbots, which is vibration-based low-cost bots for thousands unit experiments. We also have Epoch 2. It's a high-precision academic robots with rich sensor suits. Then some people decide to make their own swarm unit, for example, the DIY swarm. They use ESP32 based nodes for hands-on learning. Then we'll make building a DIY swarm node. First, we use a microcontroller, which is the use for the ESP32 for native ESP now protocol, allowing ultra-low latency direct communication. Then we also use sensing, for example, HC SRO4 ultrasonic sensor or IR proximity module for detecting neighbors, bots, and obstacles. Power: single cell LiPo batteries, 3.7 volts, combined with TP4056 chargers for efficient small footprint energy. Then we have chassis. A 2WD mini reuse chassis preventing snagging and allow for differential drive maneuvers like spinning in place. As you know, this is quite interesting, but I choose my own design, so that can change. What is the learning roadmap? The learning roadmap is that we first start with theory. We learn about Reynolds voids and decentralized state machines. Then we go to simulation. We build and test logic, Argos and NetLogo virtual worlds. Third, we prototype. We make our own bot and test basic obstacle avoidance. And four, we scale up to multiple units and how we can make it into an emerging global behavior. What are the real application for this? What are the application for this swarm robotics? Well, my friends, from laboratory curiosity to industrial revolution, swarms are now deployed to logistics. Thousands of robots coordinate in smart warehouses. They all work together to manage the goods in the warehouse. That's if you look at Amazon, for example. That's one of the main example. They use robots to manage the inventories. Environmental monitoring. Many use multiple robots to monitor ocean health and reforestation. And disaster relief. This is the most significant one. Search and rescue in unstable structures. Because in disaster relief, the robots can easily get destroyed by rubble, debris, mud, water, acid, heat, anything. But using a simple expensive robot won't go. So instead, you use thousands of cheap robots. And when you use these 1,000 cheap robots, losing a couple of them will not result in a mission failure. It will continue until you find the desired target. So, what are the question and answers? Thank you for exploring, and see you in the next time. So like and subscribe to this video. See you next time. Swarmsara Gateway is out for the next.